Okay, so today we're going to move on to a new concept called logarithms. This is really going to build off of what we've learned the last couple of days about exponential functions. Here we go. So we're starting chapter 8 today. Chapter 7 was really quick. We covered it in just 2 lessons. That being said, of course, I did skip one middle section in there. It was just about transformations, so moving things left, right, up, down. You can have a look through it if you want, but I'm not really focusing on that. So anyway, today we're going to learn about a topic that connects directly to exponential functions, and it's called logarithms. This is going to be something totally new, but hopefully it won't be too revolutionary and too challenging. So logarithms can be used to solve exponential equations where you're unable to find a common exponential base on both sides of the equation. So hopefully you remember from last class how to solve an exponential equation where there's a power on one side and a power on the other, is that you try to get both sides to have the same base, and then you can ignore the base and just solve for the exponent. Sometimes that's not possible though. Sometimes you can't get both sides to have the same base. And so for that, we just did graphing yesterday, but there is an algebraic way of doing it, and that's involving logarithms. Now, we're just going to calm down for a second here. We're not going to get to that today. The thing with logarithms is there's a lot of skill that has to be built before we can start using logarithms for that. So we're going to build those skills today, but that's where we're heading. So just so you know ultimately why we're learning this. We're going to spend a ton of time today solving logarithmic equations. Let's get going. So before we define what logarithms really are, I want you to investigate what a logarithm might do. So if you can get your calculator out right now, if you need to pause the video, go for it. But basically what I want you to do is I want you to evaluate those 6 logarithms that are on this page. So all you have to do is you just have to find the log button on your calculator. It's right next to the 7 button. And when you press the log, it opens it up and then automatically gives you a little bracket to punch in what's inside the log. So for this very first one, 10 is inside the log. So we can say log of 10, close the bracket off and then press enter and see what it gives you. I want you to try these ones on your own. You can pause the video right here. And now I'm going to go over it. So log 10 actually equals 1. That's kind of interesting. Log 100 equals 2. Log 1000, you might see a pattern here, equals 3. Now log of 0.1 is a little bit different. Log of 0.1 is equal to -1. Log of 0.01 is -2. Log of 0.001 is -3. I want you to make a prediction about what you think that logarithm button does. It might be clear to you, but it might not be clear to you. I want you to notice that we could think of 0.1 as being 1 over 10, and 0.01 being 1 over 100, and 0.001 being 1 over 1,000. What do you think the relationship is between these numbers and the answer? Well, let me help you out. So the relationship here is log of 10 is 1 because 10 to the power of 1 is 10, right? Okay, watch the next one. 10 to the power of 2 is equal to 100. For this one, 10 to the power of 3 is equal to 1,000. If we look at this next one up here, 10 to the power of -1 equals 0.1. So there's a relationship between this 10 right here, the thing that the logarithm was equal to, as well as what number was plugged into the logarithm itself. Now this 10, you might be wondering, well, why are we pulling 10 out of anywhere? Why is this something we're doing here? Well, that we're gonna have to get into a little bit later. Another thing that you could have done as a prediction is you could have said, oh, how many, what logarithm does is just it spits out how many zeros there are in the number. And that's a pretty good approximation as well, especially with just a normal log. We'll talk about other kinds of logs a little bit later. But yeah, that is a good prediction. Anyway, let's move on. So logarithms, here's the more formal definition. Logarithms are the inverse of exponential functions that have the same base. So the relationship between an exponential function and a logarithm is you just switch things around, there's a big swap. Now, when we were talking before about just a normal logarithm, logarithms are supposed to have a base, and the base is just written as a subscript right next to the log. But if a logarithm doesn't have a stated base, you assume it's just 10. So in other words, when we said log 100, really that's saying log base 10 of 100. That's where that 10 was coming from before. When I just go back real quick, that's why all of these were compared to a base of 10 in an exponential. It's because the base of the log was all 10 on every single one of these. Anyway, I'll just go back here. So again, if a logarithm doesn't have a stated base, you assume it to be 10. Logarithms can be used to solve for unknown exponents. An exponential function can be rearranged into a logarithm and vice versa. Now this little animated picture here shows it pretty well. It's just a big switcheroo. Now what I always find easiest to deal with these, the way I always remember this and what I always start with, is I look at the base of each of these. The base of your exponential function becomes the base of your log. Okay, so the base of the exponent is the base of your log. So base becomes base. That's a pretty easy one to remember. Now the other numbers are a little bit more obscure. I like starting with my exponential just because that's the way my mind works. The answer to the exponential function becomes the input to the logarithm. So the output of the exponential becomes the input of the log. That's why they're the inverse. You switch the output and the input, right? Another thing you could say is the actual exponent on the exponential function, that becomes the answer of the log. That was your input, it becomes your output, or vice versa, however you want to look at this. Bottom line is always start with your base. It's the easiest one to begin with. All right, so for a first example here, if log 32 is equal to that huge number, then what is 10 to the power of that really big number there? Or I guess long number, really. It's not a big number, it's 1.5 something, right? But anyway, what I want to kind of illustrate here is the whole idea that you can go from a logarithmic equation to an exponential equation, no problem, right? So in other words, we're looking for this thing is, this is equal to some unknown. I'll just put it equal to a question mark, right? Well, let's think about what's going on here. Log 32, that's really log base 10 of 32. So if we think about turning this logarithm into an exponential, we would have to say that 10 as the base of our log becomes the base of our exponent. The answer to that logarithm becomes your exponent itself, so it's that 1.50 yada, yada, yada. And the input of the logarithm becomes the output of your exponential function. So in other words, to answer this, what is this? Well, it's 32. The output of your exponential function is the input of your logarithm, as long as everything else has stayed the same. It's just a big switcheroo. Let's do some more examples. So this one is really good. It's going to be getting us to go from exponential to logarithmic and vice versa. Let's start with this first one. In exponential form, 4 to the power of 2 is equal to 16. Remember what I said before. Always start with your base. The base is 4, so I know I'm going to have a log with a base of 4. Now, what's going to be the input of this log? That's always the question. Well, the input of the log is the output of your exponential function. So this is going to be log base 4 of 16. So that's the thing actually being plugged into your logarithm. And that equals the input of your exponential function. Input, of course, is talking about your original exponent. So that's going to equal 2. So 4 to the power of 2 equals 16. It's just a big switcheroo. Okay. Now, just something that just came to mind right now. You might be wondering, how do you put a log base 4 into your calculator? Well, I'll tell you right now, we're not going to worry about that today. There is a way of doing it. It is actually kind of weird, but we'll talk about that another day. Don't worry about it for now. Your calculator only has the log button, and that's a log base 10. We'll have to get away with a different way with that, but again, don't worry about it for now. Anyway, logarithmic form of log base 5 of 1 equals 0. Again, start with your base. Your base is 5, so I'll say base of my exponential function is 5. The output of your logarithmic function becomes the input of your exponential function. So 5 to the power of 0 equals, the answer here is going to be whatever is the input to your logarithm. Well, that equals 1. And that shouldn't be a surprise either, because 5 to the power of 0, anything to the power of 0 is equal to 1. So that really shouldn't be a big surprise there. All right, here's another one, logarithmic form, log base 9 of 3. Again, start with your base. So 9, your output becomes your input, so 9 to the power of 1/2 equals the input of your logarithm, which is 3. And this hopefully makes quite a bit of sense as well, because remember, when you have an exponent of 1/2, that's like just saying the square root. So the square root of 9 is 3. That works just fine. All right, we're going to go backwards again. So exponential function, 5 to the power of 3 is 125. Start with your base. Log base 5. Your output becomes your input, so log base 5 of 125 equals 3, right? Just a big switcheroo. Last one, start with your base. 3, exponent, -3, equals the input, 1/27. And again, that shouldn't be a surprise either, because 3 to the power of -3 is like 1/3 to the power 3, and 3 to the power 3 is 27. Boom, we got it. All right, so here's another series of examples, just a bit of a hint here. When changing from exponential form to logarithmic form, your power, so the whole thing, should always be completely by itself first. Okay, no things multiplied or added or subtracted or whatever to it. Get your power all by itself. So let's see some examples here. Change to logarithmic form. We have a bunch of exponential equations. Let's change these. First things first, 5 to the power of x, that piece right there is our power, but this 3 is just a coefficient on the outside. Let's divide that away. Y/3 equals 5 to the power of x. Now that we have our power all by itself, we can change this into a logarithmic form. Start with your base. The base is 5. So we have log base 5. The output to this, so what your power is equal to, becomes your input. So log base 5 of y over 3 is going to equal, well, your original input. So it'll be x. So again, your base becomes your base, your log. The answer to your exponential function becomes the input of your log. And the input of your exponential function, namely the x, the actual exponent itself, becomes the output of the log. So that right there would work. Same with this one. Let's get our power all by itself. So we're going to have y plus 9 equals 4 to the power of x. Now that your power is all by itself, start with your base. 4 is our base, so log base 4. The output becomes the input, so y plus 9. And then that is going to equal x. Whew, okay, good. Let's keep moving. All right, so now we're kind of entering the whole gauntlet of questions that we're going to be doing here. This is where it's going to get a little bit more extreme. These questions, however, on this page, they're not too bad. These ones are like pretty entry level. If you want to try these ones on your own, I would really appreciate it. You can pause the video here, but I'm going to go over them in case you don't, or if you've already gone over them, great. So here we go. So solve for the value of x. Log base 3 of x equals 5. Looking at it like this right now, it's like, okay, what the heck? How are we going to get the x out of the log? My whole point here is, though, oftentimes it's easier to change to the other form, because then you can maybe see what's going on a little bit better. So let's start with our base. The base is 3. The exponent's going to be 5, and that equals x. Well, now we can solve for x, no problem. We just have to put in 3 to the power of 5, whatever that is, right? So 3 to the power of 5 is equal to x. Let's get a real number for that. 3 to the power of 5 is 243, so I'm going to say x is equal to 243. Great. All right, now the next one. Log base x is of 64 equals 6. This is a really weird one, because this is saying that x is your unknown and it's your base or your log. That's a really, really strange one. Well, let's rearrange this. Start with your base. Your base is going to be x. Your exponent's going to be the answer, so 6. And the input of the log becomes the answer to your exponential function, or the output of your exponential function. So x to the power of 6 equals 64. Now this one, it might be tough depending on where you're at right now. But in order to find x, we would have to take the, I guess, the 6th root is, I guess, what we would call it. So in other words, we have to take the 6th root of both sides of this. To take the 6th root, that's a little bit of a weird one. In your calculator, you should press 6 first. And then if you press math and you scroll down to, there's one where it's like x and then a root sign, that's going to make it the 6th root. If you have a TI-84, it might be a little bit different. But anyway, the 6th root of 64 is equal to 2. So in other words, x is equal to 2. Because the 6th root of x to the power 6, of course, that cancels those out. Ooh, I totally missed those. It cancels those out, and you're just left with x is equal to 2. Good. All right, last one here, at least on this page. There's going to be a lot more after this. Log base 3 of 81 is equal to x. Rearrange this. 3 to the power of x is equal to 81. Now, if it weren't for the lessons the last couple of days, you might be scratching your head here and going, oh, no, what on earth? What's the x up here? How do we solve that? Like, do we have to guess and check or what? Well, no, you don't have to guess and check. Do the old trick that we had from last class where you get both sides of the exponential equation, because that's what this is. It's an exponential equation. Get both sides of that exponential equation have the same base. Well, 81 can be written as something to the power of 3, or 3 to the power of something. Sorry, 3 to the power of something, right? We have 3 to the power of x is therefore equal to 81, which is 3 to the power of 4. Now what we can say is we can just ignore our bases and just look at our exponents, and that actually solved it right there. X is going to equal 4. See how it all kind of ties together? These two logarithmic and exponential function forms can be used in tandem with one another to find our desired solutions. All right, next ones, again, if you want to give these ones a try, these ones are a lot more complicated. So you can give them a try if you're feeling bold, but if you're not, here we go. Log base 2 of -4 is equal to x. All right, we want to solve for that x there. If there was a way to plug this in our calculator directly, we'd be good to go right now. Like if you could do this directly, and I'll tell you right now, there is a way to do it directly. I'm just not going to teach it to you right now because I want us to rearrange these and not worry about that. We'll get to that later. And the reason I'll teach it later is because there's an explanation as to why it works. Don't worry about it for now, though. Don't worry about it. Anyway, here we go. 2 to the power of x is therefore going to equal -4. So 2 times itself, x number of times, is going to equal -4. Well, you really got to think about what this really means. I mean, you could try to like get it so that both sides of the equation have the same base and all, but here's the thing. 2 times itself, x number times, is never going to equal -4. You can't have a positive number times itself a bunch of times to make a negative. It's not going to work. There'd have to be a negative stuck in there somewhere. So this one's a bit of a trick question. This one, we can actually say NA. no answer, or not applicable, or whatever, right? There's no solution. Maybe that's better. No solution. This one's impossible. There's no way that this would ever work. No solution. Told you it was a trick question. Let's try this next one. Log base 2 of 0 equals x. Okay, let's see how this one works. 2 to the power of x equals 0. So 2 times itself, x number of times, is expected to equal 0. Do you think that's ever going to happen? Hope not. It certainly is not going to happen. So again, NA, or in other words, no solution. There's no solution to this one either. That's kind of interesting. Taking the log of a negative number didn't produce a solution, and taking the log of a 0 also didn't produce a solution. That's not a coincidence. You cannot take the log of a negative number for the reason that we showed here, and you can't take the log of 0 for the reason we showed here. Those will never work. So just so you know, can't take the log of a negative or of a 0. It just doesn't work. All right, next one. Log base 2 of 1 equals x. Well, let's see if this one works. All right, so 2 to the power of x is equal to 1. Now this one, you might also be scratching your head. You might be saying, okay, 2 times itself, how many times is equal to 1? You might give up, but wait, there's a really weird one that's actually defined this way. What power will make something equal to 1? Well, the power is going to have to be x is equal to 0. By the definition of the power of 0, it'll always equal 1. So 2 to the power of 0 would equal 1, just like anything else to the power of 0 would equal 1. So x is equal to 0 is an answer. So it is okay to have 1 as a number that we put into a log. There's nothing wrong with that at all. It does happen. All right, moving on. Solve for the value of x. Oh my goodness, that first one's just insane looking, but hey, we'll deal with it, right? If you want to try these, go for it. 5 to the power of log base 5, 7 equals x. If you had a way of plugging log base 5 of 7 in your calculator, you could plug this in your calculator and go for it, right on, right? So that's fine. But there's another way of doing this. The other way of doing this, I think, would honestly be to try changing this into a logarithm, okay? I know that sounds a little bit weird because we've been changing everything to an exponential and then solving it, but let's try changing this into a log just for fun. Notice the base of this log, not this log up here, I mean the base of this exponential function, but don't worry about the log up here. The base in this situation is going to be 5. So I'm going to start by saying it's log base 5. Now the output becomes the input. So log base 5x, the output becomes the input, equals the input becomes the output. So that equals log base 5, 7. Now use your detective hat here for a second and think, okay, log base 5x equals log base 5, 7. What on earth could x be? Well, clearly, log base 5 of something equals log base 5 of 7. You just answered it by just saying that. X must equal 7 in that case. So what's kind of interesting is if you take a power of a log that has the same base as the power that you had in the first place, it's like an inception thing that goes on here. You can just cancel these out directly and just left with 7 equals x. Okay? It's a very weird one. It doesn't come around very often because nobody in their right mind puts a logarithm in an exponent. But whatever, it happens. Okay? All right, what about this one? Log x equals 1. Aha, remember, when there's no base listed, the base is 10. Oh, this one's baby food. No worries. That means it's 10 to the power of 1 equals x. 10 to the power of 1 is clear. This is x is equal to 10. Boom, easiest one we've done so far. Although maybe not, because again, sometimes people forget that if I don't list a base, the base is 10. Okay, just make sure you don't forget that is what I'm trying to say. All right, next one. Find the inverse of the following equations and express your answer in the form y equals. So just a throwback here again, we've mentioned inverse even in this lesson. We've said a logarithm is an inverse of an exponential function. This is hopefully going to illustrate this a little bit better. Earlier on in this year, when we first learned about inverses, we learned that inverses are really just where you swap your x and y. Okay, so we're going to do that for both of these. Let me start with the one on the left here. Start by swapping your x and y, because that's what taking an inverse is. X equals 2 to the power of y. That's the inverse. That is the inverse of this. So we've already taken the inverse, we're good to go. But the thing with inverses is, remember, we always said swap your x and your y and then rearrange and get y by itself. That's what we're doing here. We want to get it in the form y equals. Well, there's not really a way to get this exponent of y out of here. Not directly, at least. So we're going to have to try turning this into a logarithm and seeing where it brings us. The base here is 2, so we're going to say it's log base 2 of the output, which is x, equals the input, which was y. Well, there it is. That was just one step right there. No big deal. So log base 2 of your answer equals your exponent. Your exponent's y. Boom, right? That's why we always said these are inverses of one another, right? So a logarithm is just an inverse of the exponential function. So this was the exponential function. If we took the logarithm of this, it just flips it around and you get the inverse. Okay, moving on to this one. Y is equal to log base 4 of x. Well, let's start by taking the inverse. X is equal to log base 4 of y. We want to get y by itself. Looks like the only way we can do this is turn it into an exponential. So the base is 4, the exponent is x, and the answer was the old input of y. There it is, not a big deal, right? So again, they're just reciprocals, sorry, there's just inverses of one another. A logarithm is the inverse of an exponential and vice versa. Cool. So, summary, a logarithm is the inverse of an exponential function, literally what I just said. An exponential function, or any exponential function, can be written as a logarithm and vice versa. They are inherently related to one another, and they are exceptionally useful when you use them in tandem. Now, some of the little things that we just found today, just by accident, well, I don't remember if we did this first one. Log base a of a, that's just going to be equal to 1. Because think of it this way. If you were to put that into an exponential form, that would be saying your base a to the power of your answer, 1, is equal to the thing you input. Well, yeah, no duh. A to the power of 1 is equal to a, right? It works. Another one, log base a of a to the power of n. It's just like it all cancels out and you're just left with your n, right? So if we wanted to rearrange this one as well, start with your base, and then your answer, a to the power n, equals your input, a to the power n. Yeah, no duh, it works, right? Same with this one. We did look at this one. I know that for sure. Log base a of 1 equals 0. That's because a to the power of 0 equals 1. I'm not even going to write that out. We also looked at this one as well. These ones are really uncommon. A to the power of log base a of n is equal to n. So it's like, why on earth, when you have the same base in a logarithm and the exponent of your exponential, like holy smokes, why on earth would you even do that? You're just left with n is equal to n. You're good. The other thing that we found today was you can't take the log of 0 or of any negative number. That's really important. You're not going to get an answer there. There's just no solution. It's just outside the domain of our function. Okay? Anyway, we're done. So for practice, I want you guys to do these questions. There's quite a few of them. But again, logarithms are really, really important. This is a skill that you have to build. I don't think this will take too long, hopefully. These are some of the more basic questions. This one's just kind of thrown in the middle. And these ones are a little bit more advanced, but I'd like you to give these a try. The other thing is, you'll notice I'm really jumping around with these questions. We did not talk today about how to graph logarithms. I'm not super sure whether or not I'm going to insert that anywhere because I don't know under this current situation if that's something that's absolutely essential right now, but just keep your eye out for that. If you're interested, you could try graphing what a logarithmic graph looks like, but again, I haven't told you how to do different bases yet, so don't worry about that for now. But definitely give these questions a try, and if you need any questions, or need any help rather, if you have any questions, please contact me. Send me a message over Remind, and I'm there.